Hello, Chemistry 2341. Today we're going to start Chapter 7. So this is going to be Chapter 7, Section 1, Nomenclature of Alkenes and Alkynes. So the first thing we have to think about when we have this a double bond is the fact that we do not have free rotation around that double bond. Therefore, we have a fixed geometric isomer in the system. Now, if we have just two groups attached to that double bond, we can have a cis or a trans isomer, like shown in the bottom of here. So if we just have two groups associated with it, if they're both on the same side, they're cis, but if they're on opposite sides, they are trans. However, this does not work if we have more than two substituents on that double bond. For example, in the presence of this, we have 1, 2, 3 different groups on that double bond, and therefore our cis and trans do not work. Okay, so now we have to think about what are ways to definitively define what the different geometric isomers would be. And so we do that using priority of the substituents. Just like we used priority of substituents when we were assigning R and S, we use that same style of prioritization to figure out whether they are on the same side or the opposite side. So in this case, all we're worried about is which is the higher priority on one side of the double bond and which is higher priority on the other side of the bond. We don't have to assign all four. We just have to assign one is on this side. So in this case here, we have a single carbon. Here we have a carbon bonded to another carbon. Therefore, this is the highest priority. Over here, we're comparing a hydrogen to an oxygen, and therefore this is the higher priority. And therefore, these are on the same side. And so what we can do is we can call that the Zusammen configuration or the Z configuration. So you can think about it as the Z groups are on the same side, okay? And that's an easy way to remember it. Now, if the highest priority groups are opposite each other, in this case, we have a carbon versus a hydrogen on this side of the double bond, and we have a hydrogen versus our OH on this side of the bond. We now have them on opposite sides of the bond, so they would be the Entgegen or opposite configuration, and therefore they are the E designation. Okay, let's do that again with some other different materials right here. So if we're looking at this compound right here, which is the 1-bromo 2-chloropropene right here, we're gonna again cut the double bond in half and look at one side first and then look at the other side next, okay? So now we have a total of 3 substituents plus a hydrogen. So we have 3 non-hydrogen substituents, 1, 2, 3. And so we have to take into account the idea that, okay, on this side, the highest priority thing is the one at the highest Z number. And in this case, it's the bromine. Right here has the highest Z number on this side. And let's look at the other side. So we have a methyl group and a chlorine. So chlorine is a higher Z number than the methyl group. So that makes the chlorine the highest. And so they are on opposite sides of that double bond, assuming we're cutting the double bond in this direction. They're on opposite sides of that. Therefore, this is the ZE configuration, the E configuration, because they're Entgegen, opposite sides. Okay, so now let's take a slightly more complex compound right here. This 5-chloro, 3-chloromethyl, 2-isopropyl, 2-propene, 1-ol, okay? So let's start looking at individual sides here. Again, we're gonna cut the molecule in half. We are only gonna compare this group to this group right here. And on the other side of the molecule, we're going to compare that group to that group, okay? So if we're comparing the first two right here, we have a carbon, and then we have a carbon, and then we have a carbon, and then we have a chlorine, right? So that means our carbon-carbon is less priority than our carbon-chlorine. So what we're going to do is we're going to say that this one is our highest priority, okay? So our carbon with the chlorine is our highest priority on that side. So if we assign to the other side, we have a carbon bonded to a carbon and then bonded to a carbon, okay? But we have a carbon bonded to an oxygen. So the carbon bonded to the oxygen takes precedent, and therefore this is the number 1 side of that. And so that means that the first priority on this side is this one. And the first priority on this side is that one, which means we have them on the same side, which gives us our Z configuration. Okay. So that's the difference between E and Z. And again, anytime we have two or more, we can use that E and Z naming nomenclature structure. Anytime you have three or more, you must use the E and Z. Now, if you just have the two substituents and two hydrogens, you can use cis and trans. However, the E and Z would be even more precise to use if in doubt. Okay, so let's talk about the stability of alkenes, okay? So we can look at the different stability of the alkenes, that if it is at the end of a chain, for example, if it was like this is not as stable as a one that's on the inside of a chain. So a terminal alkene is one at the end of a chain. An internal alkene is one in the middle of a chain. Okay. Internal alkenes are more stable than terminal alkenes because this internal alkene has two substituents. This only has one substituent. The more substituted alkene, the more stable it is. Okay. And also, E alkenes tend to be more stable than Z alkenes. Now, the reason for this has to do with sterics right here. So if we have our E, where they're on the opposite sides, this big group and this big group are not really close to each other at all. They're only closest to these hydrogens here, and therefore there's no steric boundary that keeps them kind of pushing against each other. However, if we have this Z configuration, now we have this big group butting up against this big group, and they're forcing each other apart slightly, and so it's slightly less stable than if we had the E configuration or trans configuration system. Okay, now how do we know this? How can we prove to ourselves that it really happens? Well, we actually can compare the heats of hydration for different alkenes to determine their stability. So the idea here is that we have the addition of hydrogen across an alkene or an alkyne tends to be exothermic, okay? And so when we can measure the difference in the heat given off by each of these reactions, we can actually determine whether it was more or less stable by how much heat it's given off. If it has less heat given off, it was more stable than if it had more heat given off, okay? So the more stable the compound, the less heat given off during the hydrogenation. So if we can think of this as our relative 0 point right here, and this would be our butene, if we had a terminal alkene right here and we hydrogenated it, it'd be about 127 kilojoules per mole given off as heat during that reaction, okay? So if we had a cis alkene for this butene, we would see that it gives off 120 kilojoules per mole, meaning the terminal alkene and the internal alkene have a difference of 7 kilojoules per mole, and this is more stable because it gave off less heat, okay? So now if we have a different isomer here, the internal, but it's the E configuration or trans configuration, it actually gives off only 115 kilojoules per mole, which is 5 kilojoules less than that for the cis. Therefore, the trans alkene is more stable than the cis alkene, which is more stable than the terminal alkene, all by the difference amount of energy given off during this heat of hydrogenation reaction. Okay, so let's talk about why this is true, okay? So we can measure it, and now we have to theorize on why it's true. So the idea here is that the higher percent S character in a bond, the more readily the atom accepts electron density. So if you think about it, an sp2 is 1/3 S character, okay? An sp3 carbon is only 1/4 S character because it has the total of 4 different orbitals involved in the hybridization, where the sp2 has 3 orbitals available in its hybridization. Therefore, the sp2 carbons are more able to accept electron density, and sp carbons are more likely to donate electron density. So that means if we have an sp3 carbon near an sp2 carbon, it's going to donate electron density to it, and the sps are going to accept that. So let's look at that in the function of different types of alkenes. And if we look here at the bottom, we see that our tetrasubstituted alkene, internal alkene, has the lowest heat of hydrogenation of around 26.9 kilocalories per mole. Okay, and that is lower than that of the trisubstituted. And so we see that there's a difference in heat and energy from that. Now, if we look at disubstituted, if they're substituted on the same side versus trans versus cis, there's a slight difference in them, but they're all approximately in the same range here. So this is disubstituted, and it has mostly to do with the ability of those sp3 carbons to donate to it. And there's a little bit having to do with the sterics of this right here. And then if we go to monosubstituted, which would be a terminal alkene, versus ethylene, which would be the least substituted possible, is the highest heat of energy in kcals per mole. The previous number was in kilojoules per mole. Okay, so that being said, that tells us that having 4 sp3 hybridized carbons attached to the double bond makes it most stable. Having no sp3 hybridized carbons on it makes it the least stable. Therefore, the thing to look for is when we can make the more substituted alkene, it's going to be the more stable of the materials. Okay, so that means that when we actually start making our alkenes, we can start getting favoritism based on how we can do that transition state. So when we first did our reactions with alkyl halides, one of the ones we did was, a dehydrohalogenation right here, where we took a hydrogen and a halide off, and so we did that with a base to form an alkene right here. And in this case, we would just have like chloroethane turning into ethylene. Okay. So we can also accomplish that with a dehydration of alcohols, where we take the proton off here, kick these electrons in, and kick that out to give us an alkene as well. And these are typically done by starting with protonation of here and then removing of a hydrogen. And so we need to think about these as elimination reactions, either a dehydrohalogenation, eliminating to give us an alkene, or a water leaving to give us an alkene in the next set of reactions. Okay, so let's talk about the E2 mechanism in the dehydrohalogenation system. So in an E2 mechanism, we have both the base coming in and starting to tug away at this electron, at this hydrogen, before the leaving group leaves. So we do not form a carbocation. So we have the base tugging at the hydrogen here, allowing the electrons to come in. And when the electrons come in and form our double bond, it allows the electrons to kick out with the leaving group. So we have our base taking away the hydrogen, and we have our leaving group leaving as an anion, okay? So we like to use the E2 as a better reaction because we do not form inner side products. If we formed an E1 mechanism, that's where we would deprotonate, or the leaving group would leave first, giving us a carbocation. We have a possibility for rearrangement. So let's look at that. So to encourage an E2 reaction, we want to use a secondary or tertiary halide if possible. Okay, the reason we do that is by steric hindrance, it'll inhibit substitution reactions. That is, a second or tertiary means that we will not do an SN2 reaction. Okay, so that does not happen when we have our secondary and tertiary materials. We can use primary alkyl halides if we use a big bulky base. And our classic bulky base is T-butoxide right here. Okay. So the reason is that this right here is so big and bulky, it can't act for substitution. There is no SN2 reaction as well. And we're forming where the base will come in and start tugging on the hydrogen first before the other group leaves. The other way to encourage the E2 is to use a high concentration of a strong base. The stronger, a higher concentration you have, the more likely it has to associate with a hydrogen before anything else happens. And this also helps prevent the formation of a carbocation, which would eliminate the E1 and SN1 reactions, because those have to form the carbocations first. And by moving even further to a strong non-nucleophilic base, like T-butoxide, also prevents this because you cannot undergo that substitution reactions. Okay. In addition, use of high temperatures favors elimination. So if you're deciding between, oh, is it going to be an SN1 reaction or an E1 reaction or an E2 reaction or an SN2 reaction, and it's done at room temperature, you can favor substitution reactions, where high temperatures favor elimination reactions. So you're favoring E2 reactions by taking a base, and in adding heat to the system, you will encourage elimination reactions. Okay, so does that mean that E2 reactions can be stereoselective or regioselective? And yes, the answer is yes, but it's not because of just where the things are or the statistics of where the hydrogens would be. It's looking at the energy of the transition state, okay? So let's look at two different options for this E2 reaction here, okay? So in this first option here, we have this methyl group and this methyl group are equivalent, and this methyl group is not equivalent to these two, okay? So that being said, we have a choice of our elimination happening with 6 hydrogens here or 2 hydrogens here, okay? Statistically, you'd think that it wouldn't take one of these beta hydrogens because there's more of them, right? Okay, so let's look at what would happen if we did that. If we did that, the transition state for that particular material would look like this. We have our base coming in, starting to pull our hydrogen away, then these electrons would be kicking in, and then these electrons would be kicking out to give us our product here. Okay, now notice our product here is a di-substituted alkene, okay? Now, let's go ahead and do it again. And instead of reacting with these beta hydrogens here, we're going to react with this beta hydrogen here instead. So our transition state would look like we have our base coming in, starting to pull the electron density away from here. These electrons are going to kick in, these electrons are going to kick out, and we have the possibility, even though there are fewer of these hydrogens available to it, that transition state actually ends up being more stable, and we make the more substituted product. This is the tri-substituted product, okay? So we have di-substituted here, and we have tri-substituted here. This is the more stable product, and because of that, this is actually the more stable transition state. Ooh, so if that's the more stable transition state, that means it has a lower activation energy than this one here. So this one has a lower activation energy, this one has a higher activation energy. So statistically, you might think, oh, there's 6 hydrogens, will go that way, but this is thermodynamically the more favored product. So let's take a look at that on an energy diagram. So if we think about that on an energy diagram here, this transition state here, right, would have the secondary hydrogen here versus the primary hydrogen here. And it actually is, the secondary has this lower transition state energy, and this is the one for the higher transition state energy, this one. And therefore, because of the lower activation energy, we end up making the internal alkene. This is true for any of the systems. Every time we can get a tetrasubstituted is going to be more stable than our tri-substituted, and then our di-substituted are about the same for the on one side versus trans. This is a little bit less, our cis is a little bit less, monosubstituted and non-substituted here, okay? So it all has to do with this transition state having a lower activation energy, therefore it becomes the major product. So thermodynamically, you're trying to get a more substituted alkene. All right, and that will complete our section 7.2.